Master Burgoyne. I'm a musicologist, originally American, but now in Amsterdam for a long time. And I do a lot of work with music and AI, and I also do a lot of work measuring musical behavior. And that's when I do a lot of psychometrics and I do a lot of STAN. So I want to talk to you today about incorporating response times into item response models, a case study with special functions in STAN. But I want to start by testing your musical memory. So it's a real pleasure to be here in Sweden because this is, of course, a place where people care so much about music. One fun fact is that people in Sweden in particular love Christmas music so much that, so far as I know, it is the first market in the world where Spotify flips the switch to start having you search for being able to find Christmas music when you do a search. So I'm going to have you do an experiment we've done online with hundreds of thousands of participants at this point. You need to listen to a little fragment of music, try to recognize the song, and start following along in your head. Don't shout out the answer, please. After a few moments, the sound is going to mute for 4 seconds, but the music's still playing on my laptop. After a few moments, the sound is going to mute for 4 seconds. The music's going to keep playing. And then sometimes during the mutes, I might skip forward to a different section in the song. And when the sound comes back, that's what you need to figure out. So did the music come back exactly in the right place, or did we actually skip during the mute? So let's just try 2 examples. How many people think it continued in the wrong place? Yeah, okay, that's an easy one. One of the best-known Christmas songs of all time. This one will be a little trickier for some of you. Swedish people, or Swedish culture, treasures not only the Christmas canon, but also the Eurovision Song Contest canon. So for the Eurovision fans out there, whether you'll admit it or not, let's see how you do with this one. We are the heroes of our time, heroes! How many people think that continued in the right place? How many people in the wrong place? Okay, that one's about 50-50. It's hard. It was, in fact, in the right place, in that case, and that was Mons, of course, Heroes by another one I'm not talking about today. Arguably, if you do a proper preference model, the most beloved Eurovision winner of all time by the juries, the general public, and everyone. But when you collect data like this, you have to deal with the fact that playing a game like this, people are always making a speed-accuracy trade-off. And that really pushes against traditional advice, hopefully becoming less traditional, which is that you should model accuracy and response time as 2 separate models completely independent of each other. That's what a handbook of item response theory will tell you to do. But the typical reality, certainly in an experiment like this, is that faster responses, it seems counterintuitive, but faster responses, perhaps more confident people, tend to be more accurate. And you also have a very common confound in the form of individual differences in that some people just like to play games very aggressively, answer very quickly, make more mistakes. Other people are more conservative or wait longer before they make an answer, even though their underlying ability may be exactly the same. So if you model accuracy and response time independently, you don't have a prayer of finding any of that. So what are you going to do? To give an example of actually what this looks like, here are some recognition times from that experiment using dot plots. Actually, I changed that after the talk, on the first day, representing 50 different draws in each case, and you see that the correct verifications are indeed the fastest. Incorrect verifications just ever so slightly slower, and it takes people actually quite some time to finally realize that they just don't think that they know song. So what do you do if you actually want to incorporate speed and accuracy jointly into your model? The classical, or slightly less traditional solution would be to choose some kind of a scoring role. And as we've also seen in this conference, score is one of those words in statistics that can mean so many things. But I mean score in the sense of a game, but as a feedback I'm going to give you if you're trying this musical experiment. And 2 classic examples for an experiment like that would be something called the correct item summed residual time. So you have a time limit. When I do that game online, people usually have 15 seconds to recognize. So the correct item summed residual time, every time you get something right, you get however many seconds you had left on the clock as your score, and that will add up over time. There's an alternative, a little nastier, but tends to give you a sharper result, called signed residual time, where you get the sum of the time remaining for all of your correct answers, but then you lose the time remaining for every incorrect answer. So it's a way of kind of penalizing mistakes. And then the idea of having a scoring rule like this is then you want to choose some kind of joint speed accuracy distribution where this scoring rule that you wanted for thinking about your experiment, that you're giving your participants as feedback, is also a sufficient statistic for the distribution that you're using. And then you have a very, very nice setup where you can go back and forth monotonically between your parameter estimates and in theory, your raw scores. So far, so good. And what I want to introduce in that talk to those of you who don't know it, sell a little bit, is the generalized inverse Gaussian distribution. It sounds like a bit of a mouthful, but it's a very flexible distribution on the positive reals that has sufficient statistics in log time, regular time, and speed. And that really helps if you want to explore a space where it just isn't intuitively obvious from day zero, do I actually want to be thinking of these response times in terms of a typical log time model or a regular clock time model or a speed model? Many well-known distributions are special cases, and although it used to be quite difficult when I first started trying it to do it in Stan, recent numerical improvements in Stan make it almost easy to use. You'll see by the end of the talk. But almost easy to use, so I called my talk Incorporating Response Time into Item Response Models, but perhaps a better subtitle would be Learning to Love the Modified Bessel Function of the Second Kind, because that's where the almost in the easy to use comes back to bite us. But we'll get to that later. I want to focus on three key things. First, just in general, what do we need for a joint psychometric model of accuracy and response time in a bit more detail? Second, what is this generalized inverse Gaussian distribution and what are its computational challenges in Stan? And finally, what is the catchiest Christmas song of all time? If it isn't Mariah Carey, what can we learn from an experiment like this? But let's start with those speed accuracy psychrometrics. So just to give you a very cartoon level one slide summary of how these things are thought about. So there is an old saying that any model that you've thought of, a psychometrician probably thought about it 20 years earlier. That's perhaps a bit less true with some of the complex things that we're doing in Stan, but there are some real classic models. One that is still used today is Ratcliffe's diffusion model in a family of process models where you try to imagine for an experiment like I just had you do, information is accumulating in your cognitive system in one way or another until finally it hits a threshold saying, yes, I know this song, or it hits some other threshold saying, no, I don't. You get for your positive responses in that case, not the generalized, but just the usual inverse Gaussian distribution, so the first hitting time of a Wiener process, but then it actually gets more complicated because when do you hit the boundary on the other side? And so the maths behind the Ratcliffe diffusion model have always been a bit messy, and they still are, but in some ways it has a very nice, strong cognitive process behind it. The other approach is a more strict measurement approach, also has been around forever, initially just with gamma distributions because they were the best understood, was just trying to define a mean structure. So if you use classic item response theory notation, we see all of the people participating in the experiment have some ability, we'll call those theta. Every item stimulus that I'm using in my experiment has some kind of difficulty, I'll call those delta. You just try to figure out what the model of the expected value of your distribution should be. And so since the 1990s, the focus was often trying to decide, is this fundamentally an additive process, a multiplicative process, or an inverse additive process, and the relationship between the participants in an experiment and the stimuli that they encounter. There's another way, a so-called rash type model, which is then looking actually per response type, so say correct, incorrect, skip in an experiment like I had you do, just trying to make a mapping between parameters and sufficient statistics in a distribution family that we talked a bit about before. In an experiment like mine, you might want a time-independent parameter, I'm called Xi, and then potentially log time,
time or speed, as we talked about before, which would correspond to whether you were thinking about times in terms of a geometric, arithmetic, or harmonic mean. And if you want to put both people and items on the same sufficient statistic, then you also have to decide whether to use an additive or multiplicative combination. Correct item residual time would be an example. I'm running a little short on time, so I'm going to skip over that slide. But then once you've decided to align parameters with your sufficient statistics, you're going to be stuck in the exponential family. That's the Pitman-Copen-Darbois theorem, is kind of a basic. And so you're going to end up with a distribution that looks something like the first line, something that has something that doesn't have to do with the parameters, just has to do with x and t, and then an exponential of your parameters. And if you have something that works like that, even in a polytomous context, you end up with a conditional response time distribution that looks actually like our friend, the generalized inverse Gaussian distribution. So what is that? It's a bit of a messy formula, but despite its messy formula, it's actually quite well behaved. It's self-decomposable if you work in a world where that matters. Again, it has sufficient statistics in log time, clock time, and speed. Special cases include the gamma distribution, inverse gamma distribution, and inverse Gaussian distribution. And it has the right tail and the right tail of the reciprocal are exponential, which tends to make it very well behaved. It doesn't tend to get out of control, except for that inverse gamma-gamma special case. Its biggest problem is that the normalization involves a modified Bessel function of the second kind, K alpha, which is in Stan, but it's a bit nasty. It also has, just so you know, there's a generalized inverse Gaussian. If you take a viabilization of this, that allows you actually to pick up the viable Fauché generalized gamma as additional special cases. At that point, you get just about every exponential tailed family on the positive reals that we have in Stan or that you've seen anywhere else. But what about this modified Bessel function? So the norming constant has one special case that's actually very easy to work with, kind of a double case. K of half has perfect closed form. That gives you the inverse Gaussian. No need to worry. There's also a very useful limit, which gives you the gamma and inverse gamma cases, where, of course, the normal limiting constant uses a gamma function. Until the beginning of this calendar year, actually running a model like this, I tried many times in Stan, using gamma or inverse gamma, you got into really frustrating problems with the derivatives of the gamma function. And I think it was mostly Sean Binky, but the whole development team finally cleaned that up in January, and it works like a charm now. So those special cases are handled. There is also a modified Bessel of the second kind function, but his problem is that it only takes integer arguments of alpha. And that connects to our last talk, connects to what Bob was just saying. All of a sudden, that means you cannot use alpha as a true proper parameter. Many have tried and failed over the years to get this working. It's a lot thornier than it looks. I think I'm now, after this conference, going to try to give it a go myself. But for now, model selection and stacking are the only way you can really get around managing the log time aspect of the generalized inverse Gaussian. So Santa, tell me, what do you get if you try to apply this to my Christmas experiment? So the model setup, you have to show a kind of little bit of Stan codes. I'm not going to go through it all in detail, but by the parameters at the fixed effect overall level actually fits the mean of the distribution and the coefficient of variation to try to orthogonalize the parameterization as much as you can. Otherwise, then you're using a typical hierarchical model, with sigmas for the different potential parameters corresponding to the sufficient statistics of a generalized inverse Gaussian. Allow those to be correlated, and then use the sum to zero factors that we also have been talking about to try to squeeze as many effective samples out as you can. If you do this, just as we wrap up, what do you get if you actually try to use over the integer values and that plus minus 1/2 special case? Can you at least get a sense of where ideally you'd like to be in the generalized inverse Gaussian distribution? The answer is yes. You can actually, up on the left, it seems like, at least for this particular experiment, somewhere around -1, which would correspond to a zero-dimensional Bessel process, the drift. If that means something to you, is something that would work. But actually, even trying to optimize somewhat, over those integers, it turns out that now that we have a gamma function that actually works very well, the Heavy-tailed, often ill-behaved inverse gamma function works very well for this experiment. Actually seems to work the best. Why does it work the best? So that's one thing I realized when I did this. If you look at just the posterior predictive checks, one thing that is not baked into this distribution and isn't really baked into any distribution is the, oh my goodness, I'm running out of time effect. What am I going to do at the end? And so you can see if you look at the actual distribution, it kind of flattens out at the end. At 13, 14 seconds, people realized they were running out of time and would often just make a guess. When you actually try to apply a more proper response time model to this, it kind of goes down, and then you see that big bump at the end, because that's where I actually tried to simulate a timeout, and things were coming up. But it sort of struggles a bit, to deal with this odd kind of heaviness in the tail that doesn't follow. But in terms of the overall response types, it does well. So the model covers the data structure well, except for the running time out of effect. Trouble is, now you have so many more parameters to interpret. The model that I actually found doesn't correspond to any of the scoring rules, we actually tried in our lab. So what have we learned? Realistic psychometric models have to be able to incorporate speed and accuracy trade-offs. Scoring rules are a powerful solution, but it's not clear always a priori how to construct them. Bayesian frameworks offer a very attractive space to explore what credible scoring rules might be, and you can use this generalized inverse Gaussian distribution to help you get there, and it's almost completely implemented in STAN, given the pieces that we had today. What's left to do? Posteriors of these geometries do tend to be pretty difficult. The natural parameters corresponding to sufficient statistics are not always the parameterization you'd really want for sampling, but for psychometric reasons, you're stuck with it. Numerical stability of the special functions is essential. The challenges that arose from the gamma function actually now seem to be fixed. That is really, really great, and I'm so grateful for it. Modified Bessel of the second kind also works fine for its supports, but it would be great to move forward so that could support the reals, because then we'd have the full generalized inverse Gaussian available to us in STAN, and that would help answer perhaps the most important question that everyone's asking: will someone finally overtake Mariah Carey's "All I Want for Christmas Is You" as the new Christmas classic? Perhaps it will be Ariana Grande. Sans tell me. That's all I have for you today. Thank you for your attention. I hope you look forward to coffee.
So thank you very much. I never thought I would see a Bessel function and Ariana Grande in the same talk, but yeah. We have time for one question. I kind of want to give it to Paul because okay, that's a Paul. Because he didn't get the time before.
I don't see another one. Now I'm going to feel ashamed. This is a bad question. But this was extremely interesting. Thank you so much. I'm a bit slow, both before and after lunch, so you might have said this and I missed it. But what is the great advantage of this over sort of a Radcliffean model or those more traditional approaches that you would use and teach in psychology as a present?
So it really comes down to how desirable you find it to be to have this link between sufficient statistics, some kind of raw score you can compute from your experiments, with a belief that that may be meaningful per parameter that you're going to estimate. That is where the Radcliffe diffusion model very fundamentally and completely fails. It's actually quite difficult to implement. You don't have any kind of straightforward scoring interpretation. I mean, there's some cool work with quotient models and things that people have done, but it really is choosing, do you want raw scores that you think are meaningful? And it also gives you, it's much easier to get to specific objectivity with a model like this also than you can with Radcliffe's model. Depending on which side you're on, you may think specific objectivity is the most important thing in the world to do science or a complete waste of your time. But again, depending on where you fall in that spectrum can also kind of help you choose between a process type model. But the biggest downside indeed, of the model that I'm proposing, except in very special cases, if you try to force a Weibull in there with a pre-learned, they really are not process models. They are measurement models, full stop. And they work very, very well as measurement models, but you do have to accept that you lose a little bit of that nice process interpretation behind, even when you use the inverse Gaussian.
Brilliant answer, thank you.
Okay, so I think in the interest of time, we're going to have a cup of coffee. Yeah, okay.